So this is going to be a video about PID or PID loops and how to use them, and more importantly, when to use them. So let's start off by defining what is PID. So PID stands for proportional integral, let's increase the size of the text box, integral and derivative control. Okay, that's what the PID control loop means. So proportional, integral, and derivative. And so we'll get to what these mean individually later on in the video, but first let's just color code them so that way it's easier to understand once we get in. And let's make this one purple. Alright, so proportional, integral, and derivative. And a more general definition is basically a tool for error management. Alright, so a tool for error management. Now let's go into the nitty-gritty of it. Okay, so suppose, and this is the most common example for when you would want a PID loop. Suppose your robot, you want it to execute a 90-degree turn. So let's paintbrush. So you want it to execute a 90-degree turn, which means if its current orientation is something like this, you want it to face this. This is your desired direction at the end of the turn, right here. Okay. However, without a PID loop, in most cases what's going to happen is you're going to have some kind of overturn. You'll likely end up over here, or depending on your speed, you'll end up further and further away as you increase your speed. And this isn't because your rev hub is reading the wrong angle or is it's like not reacting fast enough. Or I mean, it kind of is not reacting fast enough in a way, but it's mostly because the dependent variable here is time, not your actual angle. See, when you have a sensor hooked up to your rev hub, or in this case the gyro is actually built into the rev hub, it has a polling delay or it has a processing delay, and those kind of delays can really make the difference between landing on the target exactly or going over, right? So the polling rate of your gyro is almost completely is what the rev hub is completely dependent on to execute a perfect 90-degree turn, which is obviously not good. So how do we fix this? PID is, as I mentioned earlier, a tool for error management. And so in this case, this is obviously an error, and it is something that PID can manage. So let's draw a graph really quickly, and let's zoom out for this. So let's draw a graph. And I'm going to basically have it be a graph with relation to time. So time, and this is going to be your angle. Okay, so, it can execute all kinds of funky movement. Basically, this is just going to go up and down. And actually, you know what? I should probably draw like a curved line so it looks more like that. And then I need another line. And then let's just finish this guy. Make this guy go straight down. Okay, so this is, let's say, the arc of your angle. Okay, it's curving forward and then it just goes linearly downwards. If we have exclusively proportional control, what proportional control is doing is basically looking at the exact height from your angle to your desired angle. Let's say your desired angle is, and let's do this in brown. Let's say your desired angle is right here, and let's call this desired angle, right? Now remember, PID always has a target in mind, right? Otherwise, it's error for what, right? So it's basically looking at the error, how much off it is from your desired angle. And proportionally, let's say we're taking a look at this point right here. If we're taking a look at this point, well, proportionally, that point is this far above that line. And so it'll take a look at this line, and it will plug it into it'll multiply it by some constant to get the adjustment for the change in your power delivery to your motors. The second option is integral control, which is basically looking at more or less the area underneath a range of variables. So this is over time, kind of, and so is derivative in a way, but this is more so over time than derivative control. So let's go to purple. And let's say we want to pick a range of time between here, so let's go over here and over here. This is basically the area of that under the curve. And it will multiply that by, it will integrate this basically. It'll integrate this part of the curve. If you know calculus, then you know what I'm talking about. The derivative control, finally, is basically looking at the slope of your line and finding the tangent line to that. And then, yeah, basically using that as, you know what, I'll just show it first. So let's say we're looking at this point, right? The derivative of this point is, or the tangent line rather, of this point is right like this, right? And the derivative function says that as the slope slowly gets steeper and steeper, as you're going like further down like this, notice that the magnitude of the derivative control is going higher and higher. But as you get closer to the vertex, and if you get to the vertex, your derivative or your tangent line has a slope of 0, right? So this guy has a slope of 0. And what that means is what derivative control does essentially is it's looking at how fast your angle is actually changing, right? Because if it's not changing at all, right, let's say you have another graph, let's use black. So you have another graph and assume the same variables. I'm not going to write them down again. But if you have the same angle throughout the whole thing, right, if this is basically your angle, then your derivative function is just 0, right? It's only going to look at, it's just basically going to be the slope of the tangent line to this line, which is just 0 the whole time, because this line isn't changing. So derivative control is looking at how fast your angle is changing, and the combination of these three is what makes a PID loop. Now, for more information about how to program this into your Java programs or onbot Java, we're going to have links in the description below to STEM Robotics. They do an excellent job of showing how to program a gyro to make it so that you can execute perfect 90-degree turns and go along straight lines. So yeah, thank you for watching.